So in this class, I will explain about the different coordinate systems that are used in analyzing finite element problems. So here, generally the coordinate systems are classified into two or three types mainly. Here, of course, we are using the Cartesian coordinate system, which you already know. For a three-dimensional analysis, you have x, y, z as the Cartesian coordinates. A point in space is represented by the three linear coordinates x, y, z. We suppose the same thing if it is for two dimensions, then only x and y are defined. If it is only one dimension, only x is defined. And this Cartesian coordinate system is normally adopted to solve problems of straight boundary edge problems. The second one is the cylindrical coordinate system, wherein it is represented by r theta z. There are two linear measurements and one angular measurement. So these are adopted to solve problems with curved boundaries. So in that, once again, if you have only r and theta, then it is called as polar coordinate system. So where we have some problems with axisymmetric problems which you have studied in your mechanics of deformable body subject. So normally a point is represented by three linear coordinates, that is Cartesian coordinates x, y, z, or it can be two linear and one angular r theta z, or it can be two angular and one linear, which is called as spherical coordinate system, which is denoted as r theta phi. Anyway, in finite element analysis, if it is if the object under consideration has got straight boundary something like this, then we can use the Cartesian coordinate system. Whereas if it has got curved boundaries, something like this with the axisymmetric problems, then we can go for polar coordinates. Now, this is about the general classification of coordinate system. But in finite element analysis, we use three types of coordinate systems depending on the type of the problem. The first one is the global coordinate system. Global coordinate system is, as you know, any point in the element is represented or is identified with respect to a common origin. For example, here I will take this as the origin, x is equal to 0, and this is the line element, or bar element or plus element, you can say. These nodal distances of these nodal points 1 and 2 nodes, they are measured from this common origin. So this is the common origin. So this is x1. From here it is x2. So this x2 minus x1 gives the length. So this length of this element is nothing but x2 minus x1. So this is for a one-dimensional element. In the case of two-dimensional element, something like this, the global coordinate system, you have x in this direction, y in this direction. Corresponding displacements you can take it as u and v. Here only u will be there in one dimension. Here both u and v will be there. Here the coordinates of the nodal points of this quadrilateral element, they are taken as 1, 2, 3, 4, and this node the coordinates will be x1, y1, x2, y2, x3, y3, x4, y4. All these coordinates are measured with respect to this common origin. So that is the meaning of global coordinate system or system coordinate system. So one thing is it has got only single global origin. In this case, this is the single global origin. In this case, this is the single global origin. In three-dimensional also, you can have a common origin. The second point is points are measured from the single origin. So that means points means coordinates of the points are measured, all the points are measured with respect to this single origin. Then we say that it is global coordinate system. The second one is the local coordinate system. Sometimes this is very much useful when we have inclined members. So inclined members like this, for example, a plus member may be inclined like this. Then it is better to go for local coordinate system. So in local coordinate system, separate origin is taken for each element. So for example, if the element is like this, so this can be taken as the origin for this element. If the element is like this, this can be taken as the origin for this element, like that. So separate origin can be there for each element, that is one thing. Then orientation of the element is not considered. So whether it is inclined, horizontal, so that along the length only, along the axis of the element only, you can take that x-axis. So this itself is, we can take it as x-axis. So we are not worried about the global sense. So in the global sense, the horizontal here is the x-axis, vertical becomes the y-axis. Whereas here it is not like that. Along the inclined direction only, along the length, along the axis of the element only, you can take it as x-axis. So that is the meaning of that. So here, and the third one is origin is located either at the end or middle of the element. So you can choose the origin at the end. For example, this is a one-dimensional element, bar element, where this is the end, this is the end. These two are the nodes, 1, 2 are the nodes. I can take this one itself as the origin. Node 1 itself as the origin, that means x is greater from this one only. So if you take this length of the element as L, then x is equal to L here at the node 2. That is the meaning of that. So if you take the midpoint as the origin, then what happens? This is the total length is L. So this will be L by 2, this will be L by 2. Then what we can write here is the coordinates of this will be now minus L by 2. X is equal to minus L by 2, whereas the coordinates of this will be x is equal to plus L by 2. Either you can choose midpoint of the element as the origin or one of the nodal points, n nodal points as the origin. So now coming to two-dimensional element, so it is taken like this. Your u and v will be there along u or x and y directions as usual. So you will be having you can take one quadrilateral element here for two-dimensional element. So 1, 2, 3, 4 are the nodal points of this quadrilateral element. If I choose the center of this element here, center of this element or centroid of this element as the origin, then through the origin you can have two axes of reference. One is parallel to this r-axis is parallel to x-axis, s-axis is parallel to y-axis, and with respect to that you can measure the distances of these coordinates. So that is another way of writing the local coordinate system for 1D and 2D. So irrespective of orientation of the element, along the length itself you can take it as x-axis, and perpendicular to that you can take it as y-axis. That is the case of local coordinate system. Now the third one is the natural coordinate system. Sometimes this is also used. Natural coordinate system, what happens? The point in an element is specified by dimensionless number. So it will not have any units. So the dimensionless number value lies between -1 and +1. That is very important. So in the case of a natural coordinate system, for one dimension, we call the natural coordinate as zeta. For if it is two dimensional, then zeta and eta. Then if it is three dimensional, zeta, eta, and mu. So all the three we are going to use. So here, what I have taken here is, this is once again a bar element. So wherein 1 and 2 are the nodes, and at the midpoint I have taken as the origin. So this is the origin, and I have taken at the origin zeta is 0. Zeta is 0 here. To the left of zeta, of course, it is negative. To the right of this origin, it is positive. That means the maximum value to the left here, I have taken -1. To the right maximum value is +1. So if you take any point here, for example, here if I take the midpoint of these two, then zeta here will be -0.5 or -half, whereas zeta here will be +half, because this is 0, this is 1, half average of that is since it is the midpoint of distances, it will be +1. So anyway, if you take the coordinate at any point of the element, the value lies between -1 and +1. So suppose the same thing for a two-dimensional element. So as you know, you have two displacements u and v along x and y directions. So here, similar to this, if you take a quadrilateral element, 1, 2, 3, 4 are the nodal points, and here the origin is taken here. Please note that origin is the center of this quadrilateral element. parallel to x-axis, if you draw zeta axis, parallel to y-axis, here you have eta axis. So zeta, eta. So this is zeta pronunciation. This is eta. So now here in this case, since we know that the maximum value of natural coordinate is +1 and minimum value is -1, so what we can write here is, if you take this as the origin, that is 0, 0, then what happens? So this point, now if you write the coordinates of this point, this will be x, zeta is positive, eta is positive, so 1, 1. So this coordinate is zeta, eta. So similarly, if you take this point, so here zeta is -1, eta is +1. Okay, this point both are -1. Zeta is -1, eta is -1. Here if you take for node 2, zeta is +1 and eta is -1. Okay, so like that you can write the natural coordinate system. So here for analyzing the finite element problems, either you can use global coordinate system wherein all the points are taken measured with respect to a common origin, or you can use local coordinate system where for each element you have a separate coordinate system and a separate origin for each, and orientation doesn't matter, or you can go for natural coordinate system wherein the value of the natural coordinate zeta, eta or nu, whatever it is, it won't exceed +1 and it will not be less than -1. So it will always lie between -1 and +1, a dimensionless number.